A very good morning to all. Respected Director Sir, Dean Academic, Dean Research and Consultancy, HOD Electrical Department, TechUp3 Coordinator, Guest Speaker, all the distinguished speakers, faculty members, and participants. On behalf of Electrical Engineering, Department of NIT Silchar, I would like to express our warm welcome to all for this TechUp3 sponsored 5 days online workshop on advancements in electrical engineering and academic and industrial approach held from 3rd to 7th August 2020. During this pandemic situation, hope you all are safe and sound. Many thanks for your interest towards our workshop. Our heartfelt thanks to the beloved Director NIT Silchar, TechUp3 Coordinator, and the HOD Electrical Department for helping us to organize this workshop. We are here today so that all of us involved in research, planning, and development in many parts of electrical engineering areas can benefit from our expertise on the near and long-term modern research development. So regarding the workshop, this workshop covers most of the thirst areas in electrical engineering, namely power electronics, power system, renewable energy sources, and electric vehicles. So in case of power electronics, the schedules are made in such a way that it will cover most of the power converter area and the application of power electronics towards renewable energy integration. When you go for power system area, we'll be giving one lecture on smart grid, energy management, and load frequency control. So regarding renewable energy sources, we'll be dealing with PV, solar, and wind. And the last one is electric vehicles. In case of electric vehicles, we'll go for G2V and B2G technology in electric vehicles, charging of electric vehicles, power converters required for electric vehicles, and regulations. And the sessions are framed in such a way that it will start from the basics of that topic and finally it will end up with the design-oriented stuff. And we have made sure in such sessions in such a way that for each and every topic, we'll be having both industry as well as academic people involved in that. In case of power electronics, you have both industry and academic, and for all other areas also, we have both industry as well as academic people involved in the lecture. So I would like to take the privilege to give a brief introduction of all the speakers who will grace the 5 days workshop. Starting with Dr. Sandeep N. Sir, he's in Department of Electrical Engineering, NIT Jaipur. He'll be dealing with the application of power electronics. Then Dr. J. Balamurugan Sir, Assistant Executive Engineer, Standard Co. He'll be dealing with the digital power system. Then Dr. Vijay Kumar K. Sir, he's from Department of ECE, IIIT DM Kanchipuram. He'll be dealing the application of power converters towards wind energy conversion systems. Then we have Mr. P. Arun Raj from Innovation and Wave Consultant. He'll be telling about the issues and problems, advancements, all these things in electric vehicles. Then we have Mr. Ashwik Reddy, co-founder and director KU's Automations. He'll be dealing with the topic how to build an IoT product in both hardware as well as software area. Then we have Dr. Srilakshmi Ma'am MP from Department of Electrical Engineering, NIT Calicut. She'll be dealing with the application of power converters in electric vehicles. Then you have Dr. S. Karthik Rajan Sir. He's from Relax India Limited. He'll be dealing with the charging of electric vehicles. What are the regulations we'll follow while charging electric vehicles? So those topics he'll be handling. And finally, we have Dr. Nikhil Sashidharan Sir. He'll be dealing with the issues and other solutions in DC microgrid. So these are the external speakers we have. Then while moving on to the internal speakers, we have Dr. Nidhal Sinha Sir from Department of Electrical Engineering, NIT Silchar. Sir will be taking a session on load frequency control in microgrid. Then we have Dr. NBD Chowdhury Sir from Department of Electrical Engineering, NIT Silchar. Sir will be dealing with the application, the smart grid communication systems. Then we have Dr. Amartesh Kumar Sir. Sir will be dealing with the application of power converters. Then myself, I'll be taking on basics of electric vehicles, B2G and G2V technology. Then we have Dr. Swapna Manzani ma'am. She'll be dealing with power management in AC systems. In this situation, we are overwhelmed with the huge and active participation across the country. Almost 900 participants, including industry personnel, faculties, research scholars, PG and UG students have registered for this workshop. And after filtering out, we have the total strength of 832. We are very much delighted to have such a huge bunch of dignitaries from academy and industry in a single platform. We wish all the participants can acquire a good amount of knowledge about the recent trends in electrical engineering from the workshop. Now I request the Professor N.B. Dev Chowdhury, Head of the Department Electrical Engineering, NIT Silchar, to give the opening address. Sir.
Thank you, Srijit, for your nice introduction to the program of 5 days workshop. Respected Director, sir, respected Dean RC Ali, sir, respected Equip Coordinator, Dr. Pati, all my colleagues from Department of Electrical Engineering and other departments of NIT Silchar, all the participants from our institutes, from other institutes, the faculties from other institute, the faculties and the students of our institute as well as from other institutes, and the persons from industry and other academia. We take the privilege for this inaugural session of these 5 days TechCube sponsored online workshop on the theme of advancement in electrical engineering and academic and industrial approach. This particular workshop will target the audience specifically in the field of power electronics and its control, specifically in the use of wind energy, electric vehicles, and the management of smart grid, including smart grid communications. This workshop will open up many avenues in terms of recent development and many avenues in terms of research directives. Most of the panel members from academia will mostly discuss on the recent advancement on smart grid, its technologies, conversion, and use of wind and electric vehicles. This is really an emerging and a topic of search. If you look at the most of the search in the Google Scholar these days by the faculty members as well as the research scholars, you'll find the specific buzzword that is the smart grid and electric vehicles. Another buzzword is your wind integration with electric vehicles as well as in smart grid. This particular workshop, I'm quite sure, will be helpful for many of us to set a right direction in the research and development as well as having sponsored projects. In this field, we have invited the stalwarts from different fields, from academia as well as from industry. I hope this particular workshop will be very much helpful for these 5 days. Due to pandemic, we are bound to open up in an online mode. And because of this online mode, we get lots of participants from across the country. For few participants, it is not possible to accommodate all of them in the Google Meet. Therefore, we are streaming the workshop proceedings in YouTube channel live. All the participants of this particular workshop will be able to participate, join and watch the videos and conversation through YouTube channel. I am thankful to our director, sir, for giving us permission for this wonderful workshop. I am thankful to the coordinator of TechUp3, Dr. Pati, for his kind gesture for approving this with a financial support. I thank Professor Mokaddam Ali Ahmed for his kind support from Dean Research and Consultancy. I appreciate the help of all the faculty members to make it a successful one and to plan for this wonderful workshop. I thank you everyone for joining this inaugural session. Over to Srijit. Srijit.
They're having some technical glitch.
Yeah, maybe.
Yes, sir. So issue with audio.
It's back.
Thank you, sir. Thank you for your valuable words. Now I request Professor Ekia Barbaya, sir, Dean Academic of NIT Silchar, to share his views on this workshop. Please, sir.
Okay. Thank you, Dr. Srijit.
Thank you, sir.
Good morning, respected Director, Professor Shivaji Bandopadhyay sir, Dean RC Professor M.A. Ahmed, our expert Dr. Sandeep N. of MNIT Jaipur, our TechUp3 coordinator, Dr. Sukumar Pati, all the coordinators of the workshop, dear participants, and also experts of this workshop. I am very happy that Department of Electrical Engineering is organizing this 5-day workshop on advances in electrical engineering and academic and industrial approach. So in the last few days, the other departments of the NIT Silchar are organizing and are also planning to organize various workshops. So it is a very good trend, and I hope all these workshops will be a great success. Now, regarding this workshop, I am sure that this will provide an opportunity for our students, faculty to get an updated trend of research and development in the field of electrical engineering. In the list of experts, I have seen that a good number of experts are from the industry. These will help particularly our MTech PhD students to get an idea about the requirements and trends in the industry, which in turn will help them to shape their research problem. And for this interaction with the experts, it may also lead to some collaborative projects which will be beneficial for both the industry as well as for our institute. So the success of the workshop will depend upon the level of interaction, and I wish that our faculty, research scholars will participate in the discussion for the successful outcome of the workshop. I wish again all the participants and experts for a grand success of the workshop. With these few words, I again congratulate the organizers of the workshop. Thank you. Thank you. Over to Srijit.
Thank you, sir. Thank you for your delightful words. Now I request Professor M.A. Ahmed sir, Dean R&C, NIT Silchar, to share a few words about this workshop.
Thank you, Srijit. Am I audible, Srijit? Hello. Hello, am I audible, Srijit?
Yes, sir, it's audible.
Okay, thank you. Thank you. Very good morning to everybody in this 5 days online workshop. Respected Professor Shivaji Bandyopadhyay, Director NIT Silchar, Professor A.K. Borvia, Dean Academic NIT Silchar, Dr. Sukumar Poti, Coordinator Ticket Free NIT Silchar, Dr. Sandeep Ann from MNIT Jaipur, HOD Electrical, Professor N.B. Dev Chaudhary, all the coordinators of the workshop, and all the participants, my esteemed colleagues, faculty members from NIT Silchar and other institutions. Very good morning to all of you. So I am extremely happy that NIT Silchar, in NIT Silchar, we are organizing various types of programs. Just now, our directors have opened one international conference just a few minutes back, and that keynote speakers address is going on till now. So just 1 week ago from Civil Engineering Department, we have organized one workshop, 5 days workshop again. So it gives me immense pleasure that even during this pandemic situation, we are very much active. So on behalf of institution and the NIT section, I thanks all the organizers specifically for conducting such type of workshops. And I would like to thank our director sir and on the associated administration side to give the opportunity to go for such type of things even during this pandemic session. As you know, our institutions, again, I am saying that most of the experts are from outside the institutions, and many of the experts are from our institutions. So in our institutions, we have a lot of PhD scholars, then 15 MTech programs, 3 MSc program, 1 MBA program we are running. We are running that UGRC, Anveshan, etc. As a whole, whatever I want to say is that we are encouraging research culture in the institution, and we will continue to do that. And such type of through the outcome of the workshop or the benefit to the institution will be if some collaboration goes on, that will be one of the achievement of the workshop. Out of this discussion, if anybody can select a topic for her or his research, or anybody is able to select a particular research project and write the project, send it to MSRD or other funding agency, and as soon as it is approved, those are the outcome of this workshop, I will say. The other important aspect, particularly this workshop, is that industrial approach. Normally, we used to go on academic approach in most of the workshop, but this workshop, there is an industrial approach, so that is very good thing about this workshop. And I request all the participants that they should make a strong bond. Let us use this as a platform for collaboration and industrialization of your product. With this, I wish this workshop a very successful one. Thank you very much. Thank you.
Thank you very much, sir. Thank you for your valuable words regarding the workshop and research projects. Now I request Dr. Sukumar Pati sir, Tech 3 Coordinator, NIT Silchar, to share a few words on this workshop. Sir?
Thank you, Dr. Srijit. Good morning to one and all. Respected Director Sir, Dean Academic Professor A.K. Barbuya, Dean Research and Consultancy Professor A.M. Ali Ahmed, HOD Electrical Engineering Professor N.V. Dev Chaudhary, coordinators for this workshop, my esteemed colleagues and dear participants. First of all, I must thank to HOD Electrical Engineering and both the coordinators of this workshop, Dr. Sijit A.S. and Dr. Sapna Manushi, for their initiative, planning and untiring efforts to conduct this workshop. I am sure that attending this workshop is a unique opportunity to all the participants to clear their doubts and to have new thoughts on the advancement in electrical engineering, both from academia and industrial perspective. I do also believe that this workshop will become a platform to many participants to decide their future career in the respective field. It is heartening to know that the experts both from academia and industry will deliver their expert talks in the next 5 days. For your information that we did not organize any workshop or short-term training programs under TechIF 3 almost for a year at NIT Silchar. One of the reasons is less number of participants, especially from institute other than NIT Silchar. Now, during this pandemic situation, we have again decided to organize workshop or short-term training programs under TechIF 3 by virtual mode, and we are getting huge response from all across the country. So now, as you see that the 832 participants have registered for this workshop, it shows the responses for this workshop. Further, we have taken a decision that at least 30 to 40% of the lectures of any workshop under TechIF 3 will be taken by internal experts. I do believe that with this, we can enhance the peer perception about NIT Silchar to a greater extent. Wishing a grand success of the workshop. Thank you.
Thank you, sir. Thank you for your kind words and support. Now I request Dr. Sandeep sir, guest speaker, MNIT Jaipur, to share a few words on this workshop. Sir?
Hello, am I audible?
Yes, sir.
Okay, so respected director sir, respected deans and technical coordinator, very good morning and all the participants. So I'm very glad to be part of this workshop and very happy to see the number of registrants. It's really huge. The response is very positive. And all I like to thank the coordinators for organizing the workshop on such a beautiful theme wherein they are trying to bring up or they are trying to reach the academic industry. It is very important to have both go hand in hand. So the experts, I definitely hope it will be a great learning for all the participants and for ourselves so that updated in both academia and industry. So I wish a very grand success and happy learning to all. Thank you.
Thank you, sir. Thank you very much for your words and presence. Now I request our Honorable Director, sir, NIT Silchar, Professor Shivaji Bandyopadhyay, sir, to deliver the address.
Yeah, very good morning to my dear colleagues, the students of NIT Silchar and the others who have registered for the program from different other institutions, faculties, students, scholars, as well as those from the industry as well. So after the today morning's inaugural program on the international conference, so this program itself has a different dimension, and I'll just delve on the new dimensions that this particular program that is which we are going to inaugurate now, so that is bringing up. First of all, this shows the academia industry interactions, and it is good that in the name itself, name of the program, that is the academics and the industrial approach, these two have been mixed together. The second important part that I look into is that the experts are quite young. Normally, in a program, the experts are, say, old people. So it is good to see that is the young set of experts who will be delivering or discussing talks on these different issues. Now, on the industrial approach, what I want to share with all of you is that, say, normally as a technical institute, the academics and the industry that must go hand in hand. But in a situation like, say, Silchar or the northeast part of India, infrastructure wise, so the industries are not that much in number. So obviously, that is, as an technical institute, so we need to set our path. That is how we can build the interaction with the industry. And with that in focus, and when you look into the today's field also, and as it is growing, that is the industries from an infrastructural or a stereotypical part. In addition to that, they are moving towards the research directives, the research directions. So in any domain, and new domains are coming up where industries are looking into the new innovative ideas, so that most of the industry experts of this 5-day workshop program, they carry forward the innovation in their mind. That is, they are organizations where innovation is the key. And in tune with that, that is in the NIT Silchar itself, we have put the research and the innovation as the key focus of any of our activities, whether it is the teaching learning part or whether it is the normal research activities in the laboratories or in the research projects, in the collaborative projects at the national level or at the international level. Because through this research and the innovation by philosophy, we are not only able to increase the number of publications or number of research projects, but we are able to interact more closely with the industry people, and through that the visibility of our institute, of our students, so that becomes more accessible to the industry people. The other point that I want to share with all of you is that the various topics of the discussion during this 5-day development FDP or the online workshop, the smart grids or the microgrid structure, energy management, IoT, solar PV, grid integration of renewable energy sources, or electric vehicles. Now, if you look into them, so these are not, there is nothing in today's world like, say, purely electrical or purely mechanical or purely civil kind of thing. The real world is truly interdisciplinary in nature. For example, if you look into the electric vehicles, the people in the transport engineering sector, they work on electric vehicles also from a different angle. When the electrical department people, electrical engineers work on this area, so they have a different angle to electrical vehicles, the different problems. When the charging issues, the renewable energy sources, they are trying to integrate with electric vehicles. So that becomes an area where people from the science streams also, they are working in that area. So similarly, in other areas, like say the solar area, so solar photovoltaic, or say IoT, the people in the EC or CAC domain, a lot of data-oriented approaches are also in place. So the machine learning approaches, the big data things. So the true world, there is nothing like a specific electrical or mechanical, as I am continuously saying. So the world is truly interdisciplinary in nature. And moreover, say today's international conference that you have started on modeling, simulation, and optimization, I understand for developing any cyber physical systems or any engineering systems, before we go to the physical prototype, physical system development, we need to do modeling, simulation, as well as optimization of the parameters, so that we come up with the best solution. So in that sense, that is, I know that both the programs are going to be recorded, and they will be either live streamed or streamed later in our own YouTube channel. And in order to disseminate that kind of information in the current scenario, so very quickly, so we have moved towards the YouTube channel sharing also, so that not only our students or the faculties or the scholars, but also the students, scholars, and the faculties in other institutes, they also get a chance to go through these discussions and carry on the networking on this part. And with this, again, welcoming the young industry experts as well as the experts from the academia. I wish the online workshop a grand success. Thank you.
Thank you, sir. Thank you very much for your delightful insight on the workshop topics. It's really an honor for us to hear from you. So now I request Dr. Swapna Mansani ma'am, coordinator of this workshop, to deliver the vote of thanks.
Very good morning to Honorable Director Sir, NIT Silchar, respected dignitaries, esteemed resource persons present here today, dear faculty members of NIT Silchar and dear participants. It is an honor and privilege for me to deliver the vote of thanks on behalf of Department of Electrical Engineering for the inaugural ceremony of TechU3 sponsored 5 days online workshop on advancements in electrical engineering, an academic and industrial approach. We have been fortunate enough to have the presence of our beloved director, Professor Shivajit Bandyopadhyay. Sir, I extend my heartfelt gratitude, sir, for blessing this webinar with your valuable and inspiring words. I extend my sincere thanks to respected Dean Academic Professor A.K. Barubaya, sir, and respected Dean R.C. Professor M. Ali Ahmed, sir, for enriching this ceremony with your gracious presence and valuable speech. I extend my sincere gratitude to Professor N.B.D. Chaudhary, sir, HOD of Electrical Engineering Department, for helping and guiding us in organizing this workshop. I express my sincere thanks to Dr. Sukumar Pati, sir, TechU3 coordinator, NIT Silchar, for extending his support and guidance for organizing this 5 days workshop. I like to express my heartfelt thanks to the today's guest speaker, Dr. Sandeep sir, MNIT Jaipur, and other resource persons for accepting our invitation and spending their valuable time out of their busy schedule to share their knowledge and experience with us. And express my thanks to all the participants for showing their interest to join in this workshop. I would like to thank the advisory, organizing committee and coordinators of this workshop. I express my heartfelt thanks to Dr. Naresh Babu sir, Dr. Ripon sir, and the team for constant support for all the technical arrangements of this workshop. I hope that you will enjoy all the sessions and have a fruitful learning experience. Once again, thank you all.
Thank you, ma'am. With this, we'll end the inaugural ceremony. We'll be having the first section today. That will be taken by Dr. Sandeep N. sir from MNIT Jaipur, titled Role of Power Electronics in Electrical Engineering. The session will start soon.
Thank you, everyone.
Thank you.
Thank you, sir.
Thank you.
Thank you, everyone.
Thank you, sir.
Hello, Sandeep, sir.
Yes, sir.
Shall we start, sir?
Yeah, sure.
Okay, just I'll give an introduction, and after that, kindly share your slides.
Sure.
So regarding Sandeep sir, he was born in Bengaluru. He obtained his bachelor degree in electrical and electronics engineering from BMS College of Engineering, Bengaluru in 2012. Master's degree in Powertronics drives from NIT Nagpur, and he has received his PhD from electrical and electronics engineering from NIT Karnataka. He was recipient of MHRD fellowship for MTech and PhD degrees, and is a senior member in IEEE. He is currently working as an assistant professor in the Department of Electrical and Electronics Engineering, MNIT Jaipur. He has authored more than 40 research papers in peer-reviewed journals and conferences in the area of his expertise, which include 12 articles in IEEE Transactions and 6 articles in IET Powertronics journals. His current research interests include multi-level inverters, grid-tied PV, electric vehicles. He was a recipient of the Best Poster Prize Award in the 18th IEEE National Power System Conference in 2014, IIT Guwahati. He is serving as a regular reviewer for several journals, including IEEE Transactions on Power Electronics, IEEE Transaction Industrial Electronics, and IET Power Electronics. So it's our honor to have you with us, sir. So now we can share a slide, please, sir.
Is the PPT visible, Srijit
Yes,
sir?
sir.
Okay. So very good morning to all. So this first session, this session will be discussing on the role of power electronics, and thank you, Srijit, for introduction. Role of power electronics in electrical engineering. So this is the outline of my presentation. We'll just briefly try to understand why power electronics, like what exactly we are trying to do in power electronics, and this workshop is being a kind of a tie-up between industry and academia. It is very important to have a strong knowledge, or it is very important to understand what exactly we are looking into. And power electronics is a core thing, and this being a first session, I thought like it would be good to have a fundamental understanding of what we are trying to do in power electronics and how exactly things are going up in the recent days, both in industry and academia. That will be taken up by the other resource persons, these experts in the later sessions. So this particular session will be dedicated to understanding the core idea of power electronics, and we'll try to see the few of the fundamental circuits, like fundamental circuits which are widely used in power electronics. What is the theory behind those, and how exactly the understanding of those will be helping in developing advanced systems. Then we will try to see the basic switching cell, which is a kind of integrated part in many of the power converters. Then we'll see the DC to AC converter, or which are popularly known as inverters. So what is the core idea of an inverter, and how exactly a basic switching cell can be used to realize an inverter, and what is the idea there. And then we'll extend the idea to multi-level operation, like how an inverter, like what exactly makes an inverter multi-level. So, and why multi-level, and what are the advantages, and few of the research opportunities that are possible, and research challenges that are we get to see in multi-level inverters will be discussed, so that it will help, or it will give a brief idea of what exactly happening in the multi-level inverters area. So coming to the conventional power system, we all know that power system is basically an interconnection of electrical generation and consumption of load through suitable electrical networks. So basically, we cannot have a generation station nearby the load. So this is how the conventional idea was when the power system was built. So we had the generating stations dispersed, and they were located remotely, wherein the distance between the generating station and consumers was so large that we had to have a transmission network, or an electrical network, which transfers the power that being generated by the generators, and it will be delivered to the distribution to the consumer. So this generator, what we have here, conventionally we had few of the generating ways were using the hydro. So this we already know. So it could be a hydro power plant, or it could be a nuclear power plant, wherein we use the fusion and fission technology to generate the power, or it could be a thermal power plant. So these are the widely used or conventional power generation techniques, what we know, using the kinetic energy of the water and using the thermal and the nuclear. Okay. So once we generate the electrical energy, or once we generate the power, it has to be transmitted over the transmission network, which is nothing but a simple R and L and a few C's which are distributed. So this is how the transmission network is, and that will be delivered to the distribution network. So in the distribution networks, we have the consumers who could be a domestic consumer, or he could be an industrial consumer. And kindly excuse me for the handwriting, because I have recently started using this, so kindly pardon me for that. So the distribution network basically has electricity consumers who can be a domestic, like the regular residentials, or it could be industrial. So the idea is the electricity being generated by the generators, by the time it reaches to the consumer, as we know, since it passes through the transmission line, which is a combination of R and L, there are various losses that are going to happen over the network, and those are known as the transmission losses, and hence the efficiency with which what we generate will not be the same at which what we are going to be consuming. So this is how the conventional power system looked like, and things were running fine. But however, once we started realizing that these conventional sources, what we have, like the coal in thermal power plants, the gases what we use, the nuclear what we have, is not kind of infinite. Means there is a day that once they are going to get finished off, or they are going to get extinct. So this is a graph which shows the duration over which we can expect the coal to sustain, or we can have the continuity of coal supply, the oil supply and gas supply. And you can see it's hardly another, already we are in 2020, so 180 years left for the coal to finish. So once we are up with all the sources, so what exactly can we do? So that was the idea we triggered, or which gave an instinct that we have to look up for some alternative sources. So what are those alternative sources? Those sources should be such that they should use the natural resources which are not exhaustible. So that is the idea which was taken up. So what is the solution for this? Like if you go with the conventional power system with conventional sources like thermal, nuclear and all, so one day we are going to get exhausted and we will not be having any source left for generating the electrical power. So the solution was to promote the energy consumption of this. We already know we are using in the electric form, and the main idea was to promote the generation of environmentally clean energy. So this is what triggered the idea that we have to go for such a sources which are environmentally friendly and which are sustainable. Okay. And this is one of the way. And the second thing is to save energy by more efficient generation, transmission and distribution. So this is the idea of smart grid, where we have the GTD happening in a more efficient way, unlike generating at a remote station and transmitting over the transmission line. Okay. And the third important thing is energy wastage must be prevented. So 33% of energy can be saved by economical usage. So it is very important to know, though the energy generation becomes efficient and everything, if the consumption or if the way at which the energy is being consumed is not economical or is not in an efficient way, then there is no point in having any kind of high efficient generation or high efficient conversion. Only when the consumer becomes educated in a way that the energy what he consumes has to be done in an economical way, then only things are going to work in the right direction. So it is very important to know that the usage also, the way in which the energy being consumed also matters, and it is also going to affect the total energy production. So these are the three things that we have to generate the energy using clean energy, means clean sources. Then we have to have efficient power conversion in right from the after the generation, till the consumer end, and once it reaches the consumer should be aware of the way in which it is being consumed. So we'll just try to see the green sources first. So this, why all this story is being told is because the green sources is what which made the power electronics to have such a boom. Like it started getting into a larger picture since we came out of conventional generation, where we had generators running there and the turbines fired with the coal and everything. So if those things were to be retained, then there was no much power electronics involved. Since we had sources which are not the conventional and which could not be operated in the same way how the generators are operated, so the power electronics took a huge thrust, and that is how the power electronics got into a larger picture. So some of the green sources which are widely used are the photovoltaic and the wind energy, since they're abundant in nature and they're inexhaustible. So solar photovoltaics idea is to convert the solar energy into electricity using the solar panels. So the fundamental idea I hope everyone has. And in the wind energy, we have the turbines rotating, which are coupled to the generators, electric generators, and they are going to generate the electric power. So these are the widely used green sources. And what was the problem with these is, if you look at the solar production, so this is a typical data of Rajasthan, a place in Rajasthan, that is the energy generated in a day of every month. So that is being plotted. So if we see here, we can observe that the power generated by the solar. So, okay, before I forget, if there are any queries, I request it to be put in the chat box in the Google Meet or in the YouTube, so that we can address those at the later stage. Okay, thank you. So, coming to the power generation of the solar, the solar power generation, as we all know, the way geographically things happen, the power consumption or the power generation also varies in the same fashion. But so one thing that can be observed is the PV generation, and same goes with the wind, is not predictable, or it is not going to be a constant. Unlike a generator, if we feed an AC generator with a constant mechanical input, then it is going to generate power in the same way, means it is going to generate a constant power. But however, in case of PV, we don't have such PV, the power generation is not consistent, and it is highly intermittent in nature, depending on the way in which it is getting exposed to the sunlight or the solar input. If the solar input is intermittent, as we all know, it is intermittent, and if there is some clouds and if there is some dust accumulation, it becomes much more intermittent in nature. So what we have to do, these kind of things cannot be directly connected to the grid, and we cannot have a stable or a system which can withstand these kind of intermittent sources. The grid is being built assuming that the powers on the various end is going to be continuous, or there is no much intermittency seen at those nodes. But if you have the sources which are basic intermittent in nature, these are going to affect the grid very badly, resulting in various problems like the frequency change, and there are many other issues that are going to come up if we have the sources of this kind connected to the grid directly. So what we have to do, we have to have a suitable interface. So what exactly this interface is going to do, as per the load or the requirement of the load, it is going to alter the power being drawn or the power being sourced, and it is going to match the requirement of the load. So this is the main idea, that we should have a power interface. So we came to know that we cannot have an intermittent source directly connected to the grid, since it is going to affect the various like the parameters of the grid, like frequency, the voltage, and all those things. So we should have some kind of interface which is going to take up all this intermittency, and it is going to provide the electric power to the load in a way it is required, and it will be totally under control. So this is what the idea is. We should have a power interface between these kind of sources. The source could be a wind, it could be PVI, or it could be any other kind of sources. So what you have to do, instead of directly having it given to the load, we should have a power interface. So this power interface will take care of those intermittency, and it is going to feed the load. So what exactly is the power interface? The power interface is basically a combination, or it consists of switches and the energy storage element, that is the L and C. Okay. So the idea of using switching here is to have that, since we are having the power processed here and it is an intermittent stage between the source and the load, we should have very high efficiency, in the sense whatever the power we are drawing from the source should almost reach without any loss to the load. So that can happen only if the power interface what we have here is very highly efficient. So in order to ensure that, we are going to use switches in this power interface, because we know that in the switch, like it could be any, like assume for example, we have a mechanical switch. Mechanical switch, we know when the switch is on, the voltage across it is 0, since it is a short circuit, and when the switch is off, the current through it is 0. So basically, the V and I are mutually exclusive. They will not be present at any point of time together. Right. So this is the fundamental nature of a switch, that is the V and I are basically mutually exclusive in a switch. That is, when there is V, we don't have I, and when there is I, we don't have V. So the power, we know that power is nothing but the product of V and I. So the power consumption will be, or the power that is dissipated by the switch will be 0 at any given point of time. Right. So this is the idea, that is using some switching, or using a given desired way of switching, we are going to process the power, so that as a part of switching, there won't be any power lost, right? But what is the problem with this? Once we start switching, the power becomes discontinuous. So even though the source is trying to generate a continuous power, once we start switching, the power after processing would be discontinuous. So in order to maintain a continuity, since the load demands continuous power, we are going for L and C components. The L and C components are basically used to maintain the power continuity. So they are going to store the energy, and whenever the power being processed is found to be deficient, they'll get discharged, and thus the power continuity will be maintained. So this is the basic idea. The power interface will be a combination of switches L and C. So this is what the power interface will be. So this is the core idea of power electronics. So here, what is the electronics part here? It is the switch, because it is made up of semiconductor devices. So that is the electronic part. And since it is handling the power, electric power, so it is called as power electronics. And the fundamental items, if you ask, like what are the core elements of power electronic converter, it will be only having 3 elements, a combination of these 3 elements in a defined way. So it will be switches, capacitors, and inductors. So these are the 3 core elements of any power electronic converters. So this is the basic idea, that what exactly made power electronics to get a trust is the ability to interface these kind of sources, that is the wind and PV, which are non-conventional sources, into the grid. It is only with the help of power electronics we can have these sources operating in a stable way, and which will keep the grid in a stable, which will help the grid in having a stable operation. What are the other fields of power electronics which are widely used, or like we can see it in, these are very few. There are many other applications. So these are the widely used applications. So we have aircraft power supplies. So as we all know, in aircraft we have turbines and which will be coupled to the generators, and they are going to have various kind of the operating frequency and various speeds, right? So we have the generator and we have gear mechanisms there. So basically aircraft is a combination of, we have pneumatics here, then we have hydraulics, and many mechanical systems that are associated with an aircraft. So when we have so many systems of different nature put together, definitely the efficiency or the way they are going to operate is not much reliable, and still the system is working. So the basic idea is, can we replace all this non-electric system with an electrical equivalent or with an electrical system? So that is the word, and that is what is known as the more electric aircraft. So this is the keyword, like more electric aircraft is basically the idea to replace all these varieties of energy systems like the pneumatics, hydraulics, and many gear mechanics system and everything with an equivalent electric system, like we have motors and all those things. So if in such case, the power electronics is very essential, because only with power electronics we can have various kinds of power processings required for these electrics. So the idea is to have more electric aircraft where we have a huge role that the power electronics has to play in having this aircraft, or in making this aircraft less like highly power dense in a way. You can have aircraft with more passenger accommodation with lesser electronics in it. So that is the idea of aircraft power supplies, and power electronics plays a huge role. So there is a huge role that has to be played, and there is a requirement. One of the key requirement in aircraft power supply is the power density. We should have power converters having very high power density, since space is a major constraint in aircrafts. So, and typically the operating frequency of aircraft power supplies is 400 hertz. So if you can develop converters which can efficiently generate this voltage, then it will be with high power density, then it is highly suitable for aircraft power supply. Then we have chemical industries, then we have drives, which we already know that majority, like 60 to 70% of the energy consumed by industry goes in the drives. So we have motors here, and we have many applications like paper mills, we have rolling mills. So there the motors, the available grid what we have is 230 volts, and like if it is then we have 400 volts for 3-phase. If we connect the motor directly, then it can operate at only one frequency and one speed. That is a synchronous speed in case of a synchronous machine. And if it is induction machine with some slip, it is going to operate at a particular speed. But the applications require various speed, like a rolling mill which has a very low speed. So how do we get such a low speed? Is the only way is to generate a voltage and frequency as per the application. So that change in voltage and frequency can happen only if we have power electronics in the picture, right? Then we have the HVDC application. So basically the idea is to generate high voltage DC and to transmit it over the lines. So the advantage of this is we can have two systems which are basically at different frequencies can be coupled through an HVDC. There is no frequency constraint, and as I told previously that the transmission line is basically R and L. So once we have the DC going on the line, the impact of there is no L that comes into picture. So the reactance, there is no way that reactance losses are going to happen since it is a DC. So this is the idea. But however, to generate this high voltage DC, we cannot rely on the conventional generators. Like we should have a huge DC generators, then the commutator, brushes. It will be a very big issue to have those, to have generators of such a mass. So one of the easiest ways to generate AC, which we already know, and which is very easy, and then to convert that AC into DC. So that is the easiest way instead of having a DC generation directly. So in order to convert that AC to DC, again we have power electronics into picture. So that is the way being HVDC then. So a high voltage DC is not generated by DC generator. It is basically conversion of AC into high voltage DC using suitable power converters. Right? So basically that means the power electronic system what we have, it ranges from few watts, which could be a mobile charger, which is hardly in watts, to megawatt of HVDC system, or it could be a megawatt of rolling mills or electric drives and all those things. So power electronics goes like it has a huge, it operates in a huge spectrum of powering, both the few watt load and megawatt load. So what we do in power electronics? So this is what we do. So we will be doing either of any of this operation or all of this operation. So basically, like assume we have two systems, two AC systems, which are operating at a voltage and frequency V1, V2 and F2, and we have two DC systems which are of voltage V3 and V4. Now, if the power processing is happening, or if the power is being exchanged between two sources, that is AC sources, then such a kind of converter which comes in between here, which will be doing the job of converting the power from this source to this, or the vice versa, is called as a cycloconverter. So cycloconverter is basically converts the voltage and frequency of a AC system to another voltage and frequency level. So that is called as a cycloconverter. If the power exchange is happening between AC and DC system, then it is called as a rectifier if it is happening from AC to DC, and it is called an inverter if the power is going from DC to AC. Then we have power processing between two DC systems. If the power exchange is happening between two DC systems, then it is called as a chopper, or it is also called as a DC to DC converters. Right. Then in many cases what happens, we may not be able to have AC like conversion directly. Like we have a AC source, then we cannot have another voltage and frequency directly. So in those cases, what we do, we generally rely on an intermediate stage. That is, we will convert the AC to DC, then again DC to AC. So this happens in many cases when we don't have provision to directly have a conversion from one form to another form. And the reverse is also true. Conversion between two DC can also happen from DC to AC, then again AC to DC. So these are the things what we do in power electronics. So in power electronics, the only thing that happens is power conversion. So electric power conversion from one form to another form. The only possibility is we know only two systems, that is AC system and DC system. So depending on the combination, like how exactly the power is exchanging between the two systems, we have these various converters named as cycloconverters, rectifiers, inverters, choppers, then AC-DC AC converters, or a DC-AC-DC converter. So this is the core idea what we include, like what we have in power electronics. Okay. So in order to do all these operations, or in order to perform all these tasks, one of the key elements that are required is the power semiconductor devices, because that is the switching. Means if there is no switching, then there is no power electronics. Power electronics cannot happen only with L and C. Only if there is a switching, then only power electronics can happen. Right. So these switching are being done using the semiconductor devices, which are controlled or which could be uncontrolled devices, depending on the control terminal what we have. So that is the central piece of any power electronic converter is the semiconductor devices. So knowledge of these devices is crucial to design efficient converters, right? So only if we know what kind of devices are suitable for what kind of application, then we can come up with an efficient power converters. So first we'll try to see how exactly these devices evolved in a given point of time, right? So the first device what we had is a Mercury arc rectifier in 1902. Then later on we came into the second generation. We can call this a second generation devices, which are BJT, SCR, Triac, and G2. I hope everyone are aware of these devices, right? Then MOSFET. Then now currently we are in the technology called the silicon carbide and GaN devices, that is the gallium arsenide devices, right? Or the GaN. So what is the key point is why we did not stop here. Like once we had a Mercury arc rectifier, why all these efforts were made? So why so many devices came into picture? So what is that one thing which was deficient in all these devices, or what were the things that were felt that it is not sufficient, which given the technology to this end, that is where we are currently, that is the silicon carbide and gallium arsenide. And what is the technology is moving towards an ideal switch. So what is an ideal switch? So ideal switch must have the following characteristics. So the first thing is infinite blocking voltage. What do you mean by infinite blocking voltage? That is irrespective of what the value of voltage what you apply across the switch. It should, if you ask the switch to be in the off condition, it should be in off condition without any without getting damaged or without having any current flowing through it. So that is the infinite blocking voltage capability. Then next we have no current when switch is off. Means if you say that switch is off, then there should not be any current flowing through it. Then the third is the infinite current capability when on. That is, when the switch is on, it does not matter to the switch how much current it is allowing to flow, right? Then the fourth thing is drop voltage should be equal to 0 when on. Means when the switch is on, as I already told, there should not be any voltage. So if there is any voltage, then it is carrying current, there will be power loss happening. If there is power loss, then the power conversion efficiency will get, means it will be low. But that is the idea, is to generate efficient power conversion system using switches and the LNC combination. So if that has to happen, then the power loss in the switches must be very, very minimum, right? Then the fifth point is no switching or conduction losses. That is what, when the switch goes from off to on or from on to off state, there should not be any energy required to do this transition. Then the capability to operate at any switching frequency, and the switch should not, it should not matter to the switch at what frequency it is being turned on and off. So these are some of the characteristics that we expect an ideal device to have, right? So here we have an ideal switch which is expected to have these characteristics. So all the effort, whatever is being made right from the 1902, is to come up with a technology or come up with devices which has characteristics nearby these ideal what is being listed out here. But now what the technology what we have with the SIC devices is found to have a very low switching losses, because the on time and off time is very small. So you can very easily turn them on and off with very low power losses happening in the system, right? But however, practically, if you see, any device will have a limitations on the voltage it can withstand and the limitations on the current it can carry. So none of the practical device can have infinite blocking voltage or infinite current capability, because it is all limited by the device technology. So if you go to a market and ask like, I want an infinite blocking voltage switch, then he cannot provide, because you have to specify what is the maximum voltage that you want the switch to withstand. It could be some 600 volts or 1200 volt switch, and maximum current some 600 amps. One has to specify what is the maximum value that the switch is expected to withstand. Only then we can have a realistic devices into the system, right? So these are the ideal devices. So all the technology advancement happened in order to reach this kind of device having these kind of characteristics, right? Now coming to the static characteristics, like semiconductor devices can have, like, the characteristics can be classified into two, that is the static and the dynamic. In the static characteristics is nothing but the steady state characteristics, that is once the switch is totally on and once the switch is totally off, so what is going to happen. So that is the static characteristics, or how exactly the switch is going to behave. That is the static characteristics. The dynamic is the transition between this on and off state. So that is the dynamic, how the switch is going to transit from off to on or from off to, sorry, the vice versa, right? So depending on the static, like the static characteristics, we can have these many varieties. That is, the first one is the blocking state. So this is the IV plane. That is IV plane in the sense, this is the current axis representing the current through the switch, and this is the voltage axis representing the voltage across the switch. So this is the positive voltage, positive current, and we know the quadrant operation, right? So blocking state corresponds to the state when there is no current flowing through the switch. So we have only voltages here. That is irrespective, since there is no current, and there is no current, and the switch can block voltage of either of the polarity. Means it can block either the positive voltage, it can block negative voltage as well. So this is the characteristics of a device which represent that any switch, when it is off, if it can withstand the voltage in both the polarity, then its static characteristics looks something like this. Then we have the conducting state. That is when the switch is on, the voltage across it is zero ideally. So it can carry current in either direction, either the positive current or the negative current. And such a device is expected to have a static characteristics as shown here. Then we have the unique and unique devices. So unique, what does it mean? Unique means the unidirectional current, unidirectional current and unidirectional voltage. Then we have bidirectional current and bidirectional voltage. Right? So unique and unique devices means a device if it can withstand only positive voltage, means it can withstand only, it can block only voltage in one direction and it can carry current in only one direction. And such a device is expected, or it operates in the first quadrant here, the quadrant number 1, and such a device is called as unique or uni device. Then we have unidirectional current, unidirectional voltage in the reverse direction. If it can block voltage of negative polarity and carry current in positive direction, then it operates in the second quadrant here, and such a device is called unique and uni-R, right? Then we have bidirectional V and bidirectional current. In this case, the device can withstand current, withstand voltage in both the polarity and carry current in both the direction, right? Such a kind of devices will have characteristics similar to this. Then we have unidirectional current, means current in only one direction. Bidirectional voltage means it can block the voltage of both the polarity, that is positive and the negative. Then we have unidirectional voltage, means voltage is only positive here, and bidirectional current, either of the direction. So these are the various static characteristics. Any given power device will have either of any of these characteristics, right? So we'll just try to map the typical device characteristics, what we already know. So we know many of the power devices that like the diode, MOSFET, then the combination of these IGBT, SCRs. So what exactly their static characteristics look like? That is what we'll try to see here. So this is a typical characteristic. So it is a unidirectional current and unidirectional voltage in the reverse direction. So what device has this kind of static characteristics is the question, right? So which of the power electronic device will carry current in only one direction and which will block the voltage in only one direction, that too in the reverse direction? So what is the device? So that is a diode, right? So diode operates in the second quadrant here. So how can we say that diode is the one which has this kind of characteristics? So everyone agrees that the diode can carry current only from anode to cathode, and it will block the other way around, right? So it can have current of any value along this axis, right? So that's why we have a line here drawn on the y-axis here. So we have current only in one direction. Not about the voltage, the moment you apply positive here and negative here, it gets forward biased ideally and it will start allowing the current depending on the external circuit. So the moment you apply positive voltage, that is anode positive with respect to cathode, the voltage across it becomes 0 since it is going to turn on, right? And the moment you make anode negative and cathode positive, whatever the voltage you apply, it is not going to allow any current to flow, and it is going to block any magnitude voltage being applied across it. So this is how the static characteristics of a diode look like, right? And we have the first quadrant device, that is voltage positive and current positive. So what could be the device here? It could be a BJT, right? And then we have unidirectional current and bidirectional voltage is an SCR, because we know SCR allows current in only one direction and it can block both the polarity voltage if there is no gate given, right? Then we have unidirectional voltage and bidirectional current. So this is a typical example, that is you can have with an antiparallel diode. Then we have 4-quadrant operation. So not a single device is not available which will have a 4-quadrant operation. So we have to go for the antiparallel combination of 2 SCR or anti-series combination of 2 IGBTs, right? So this will give a 4-quadrant operation. Means you can have so this total now acts like a single device, right? So since in the market we don't have a 4-quadrant device that is readily available, if your application requires device of these characteristics, then we have to go with the combination, any of this combination, right? So now this can block voltage of either of the magnitude and it can carry current in either of the direction, right? And we have a current in only one direction and voltage of both the polarity can be blocked here, right? So this is a typical example of a unidirectional current and bidirectional voltage device, right? So generic converter. So once we know the device characteristics, we'll just try to unify the things. Means if you look at any power converter, it is going to interface. As I already told, power converter is nothing but an interface between the source and the load as per the requirement, right? So it is going to interface either of these combination means. So it could be a V to I interface, or it could be an I to V interface, or V to V, or I to I. So what does this V to I means? That is the source what you're going to have here, it is of type voltage. So when I say voltage source type, that means the voltage across it remains constant irrespective of the current being drawn. And if I say the load is of current type, that means irrespective of the voltage here, either of the polarity and the magnitude, the current is going to be constant. So that is a I type load. So the power converter, it might be interfacing a V and I, or it could be interfacing I with V, or VV and I to I. So these are the only 4 combinations that are possible for any power converter to operate, right? So only sources and loads of different types can be directly connected. So if we can understand, like by applying KVL and KCL, like KVL and KCL, if you remember, so any converter or any electric network must satisfy, must obey KVL and KCL. If this has to happen, then we can ideally say that the voltage, 2 voltage sources or 2 voltage types cannot be parallel directly, right? So that is what is written here. So only sources and loads of different types can be directly connected. That is a voltage source, that is a capacitive in nature, can be directly connected to a current type load, and a current source can be directly connected to a voltage type load. We cannot have 2 voltage types connected directly and 2 current types connected directly. So what do we do in those cases? So before seeing what we do here, means in such a cases, we'll just see a switching cell. So what is a switching cell? Switching cell is basically the minimum switching elements required. So as I told here, so this is a power converter, right? So what is the minimum combination or a combination which requires minimum switching elements to have this interface is called as a switching cell, right? In order to connect V to I or I to V or whatever. So what is the minimum elements required? So that is a switching cell. So the minimum elements, number of elements is 2. You should have at least 2 switches in your power converter to interface this kind of systems, right? So that is called as a cell. So if you have if you have switch S1 and S2 in this particular fashion, then it is called a cell. If you have the same thing is redrawn here, then this is typically known as a leg. Then you can have a voltage source connected here across the leg, and you can have the current type of load going out of the circuit. So if you have to interface these 2, then you should have a minimum of 2 switches in the circuit, right? So this is one combination. The other combination is you have a switch here across the source, and you have a switch here in series with the load, right? So this is what typically it is shown here. Again, in the leg form, it is written here. So what you can see here, the conversion is V to I as written here. It is basically we are converting V to I, and here it is I to V. Means the current comes here, gets converted into voltage here. Okay. So these are the example where the same thing is redrawn here. So you can see you have a voltage source and a current type. So you have 2 switches S1 and S2, and this satisfies KVL and KCL both, because you have a switch here. If the switch S1 opens, then we can close S2 so that there is a path for this current, and there is no short circuit happening across the voltage. So we know that voltage source should never be short circuited and current source should never be open circuited, right? So we have path for both, right? Then we have, so this is basically V to I. Then we have I to V. So we have a source here, switch S2 for the current source, and we have a switch S1. Right. So when S1 opens, we'll have S2 closed so that we have a path for the current. And these 2 will not be turned on at any given point of time. Otherwise, the voltage type will get short circuit. Right. So this is fine. Then as I already told, now we had I and V and I. So these things, there is no problem in connecting them in parallel. However, we have V and V type here. So we have a V type source and then we have a V type load. So how do we interface these? Then we should have a special arrangement. So that is what I told. We have to go for a V to I conversion, then I to V conversion. So we have an inductor here coming into picture. So what do? We'll switch on S1 and we are going to charge the inductor, and then we'll switch on S2 by opening S1 and we are going to discharge that current through the voltage type. So that way we have an intermediate conversion stage of V to I, then I to V. Similarly, we have I to V and V to I, which is happening through capacitor and the switching network here. So what does this show is that if we are trying to interface two types, that is V and I, then we can have direct connection. But if we are trying to interface two V's or two I's, then you cannot have a direct connection. We should go for an intermediate conversion stage. So this should be remembered, right? So this is a basic switching cell. That is, you require a minimum of two switches. That is the fundamental power electronic converter. Means you must have two switches to realize any power conversion to happen, right? When you are trying to connect these kind of things. In a single switch, there is no efficient, like perfect power conversion that is being happening. Right? So we'll just try to apply this knowledge of switching cell to the converters which are very well known. That I presume the DC-DC converters are like everyone are aware of DC-DC converters, right? So the V to I and I to V cells are just redrawn here, right? So you have a switch, and instead of a switch, we have put a unidirectional device, that is a diode. So this is basically V to I conversion. Then we have I to V. We have a diode here, and we have a switch here. Right? So why are we doing all these things? We'll just see that these are the basic element. That is, any power converters can be simplified and it can be realized with these cells, right? So now let us take the example of a buck converter. So what is a buck converter? Buck is basically DC to DC converters, right? With V2 lesser than V1, right? So in a buck converter, the output voltage is always lesser than the input. Now, so this is the arrangement. So what do we have? We have a switching network which is interfaced with the filter elements L and C to filter out the ripple that is like in the switching waveform, whatever the ripple is that they are going to filter out, and it is going to pass only the DC. So this is basically a low pass filter which is going to filter out the harmonics, and only DC will be passed to the load, right? Now this switch and diode is again redrawn here. We can see. So this is nothing but, if you can map here, this is nothing but a V to I cell, right? So the circuit is just redrawn. So this is your switch and this is your diode, and there is no current source here. The current source is only representing that the current through the inductor will always be continuous, right? So that is the only intention. There is no external current. This is not an external current source. This is only to indicate the current to the inductor is always continuous in nature, right? So this is a V to I conversion. So basically, buck converter is converting voltage to current, right? Now, if this is the case, then one may intuitively think that the boost converter will be the vice versa, right? So what is happening in boost? Okay, let me clear this. So in boost, we have an inductor at the input. That means immediately we should know that the current here will be continuous, right? Then the output, we have a capacitor. So this is a voltage type and this is a current type. It together forms a current type and this is a voltage type. So this is basically I to V conversion. So we are going to have this cell here. So the current source represent that the current here remains continuous and it is being converted into voltage. So this is a boost type, right? So you can see they are kind of a dual in nature. We have dual in nature. So if this is the case, if we say they are dual, then operationally, structurally they are different, but operationally they should be same, right? So is it possible that we can realize a buck converter using I to V cell? We have done using a V to I here. So can we do it using I to V? Yes, it is possible. So this is the rearrangement you have to do in the buck in order to use an I to V cell, and similarly a boost converter using V to I cell, right? So here we did from I using I to V. So boost can also be realized using V to I cell, and this is the circuit here where it is shown. So simulation verification, I'll just quickly run through the simulation. Or we'll keep it at the end, right? We'll just keep it at the end because I think time is running out. We'll just try to see the rest of the things at the end. If time permits, we'll just see the simulations. So the simulation, we can see that the buck converter here and here, operationally, there is no difference. There is no difference in the operation other than the structural change that has happened. Similarly, the boost here and here, they are same. Both are boost converters, but structurally, even though they look dissimilar, operationally, they are 100% same, right? So what does it say? That is the V to I and I to V cell are dual in nature, and you can realize either of this, right? So this is about DC to DC converters. Then now we'll just get into DC to AC. This is what the inverter is all about. So what we are trying to do here is the available source is DC. So this DC source can be from a battery or it would be your solar, and the load requires AC of 50 Hertz, right? So we have an AC load which requires AC voltage at 50 Hertz. But we have a DC source. So how do we do? So what do we do? So that question will be answered using an inverter. So basically the converter what we are going to use here is going to convert, or it is going to interface this DC load, this DC source with the AC load, right? So this is the nature of the input. Assume that the input is a constant. Now, as a very crude idea, what can be done in order to make, so this is what is available, but we want an AC voltage across the load. So what we can do, we can just take the load, connect across this DC source, take the load, connect across this DC source, say X and Y for some time, so that the VDC gets applied here. After the predefined time, means after this time, you just reverse this terminal. Instead of connecting A to X and B to Y, you connect B to X and A to Y. Then you are going to apply minus VDC, right? That is negative voltage. So this you keep on repeating after every predefined time. Then we'll have an AC voltage across the load. So this is the idea. Like the core idea is to have the load connected across the source for some time in a particular polarity, then reverse the polarity for rest of the time. So this is what is happening. So this, how do we do? So this is what we will generate, that is plus VDC and minus VDC. We are going to have a waveform similar to this. But what is that we are expecting? We are expecting a sinusoidal voltage just like any AC generator, but that we can never achieve in reality because we know, in a generator, like in an AC generator, we have air gap and the machine rotor rotates smoothly in the air gap, and the flux distribution is sinusoidal in nature. So that's why we have a sinusoidal voltage generated there. But here, what is that we are doing? We are doing switching. So switching is basically discontinuous function and it is discontinuous in nature. So with this kind of discontinuity happening, we can never have a smooth running waveform being generated. So this is only an ideal waveform that is expected from an inverter. But inverter will never generate this waveform because we have switchings happening inside the inverter. The moment you have switching, there is no continuity that is being ensured, right? Now, what we are trying to see is, if this is the input, if this is the voltage what we have, and this is what we have to generate, then what should be the structure of this power electronic converter? Like what is there inside this box? So that is what we are trying to analyze here. So as I told already, that you should have a switches, or you should have a switching mechanism which can reverse the polarity of the terminals, that is the polarity of the voltage applied to the load by reversing the terminals A and B. So if that is the case, we should mechanical equivalent circuit or mechanical equivalent will be a single pole, single throw. I think this should be single pole, double throw. Sorry. So we should have a single pole and double throw switch. So this is what we require, right? Even this is DT, sorry, right? So what will happen? For some time, we'll connect the terminal A to the upper throw. Then we have terminal B connected to the lower one, T2, right? So in that case, we'll have positive here and negative. So we have VDC being applied to the load. After some time, we'll just throw the pole to the bottom here and up here. Then this will be positive and this will be negative. So we'll have minus VDC. Right. So that is what is given in this table. So if this is the combination, then what kind of power electronic switch should this mechanical switch be replaced with? So that is the question being answered, right? So this is a mechanical equivalent, or mechanically the idea of polarity reversal has been mechanically put up using a single pole double throw, two single pole double throw switch. So power electronic replacement of this is what is being answered, right? So before that, we'll just try to see what are the requirements. So the requirement is load is AC, as I already told, load is AC and can operate at any power factor. So this is what is very important, because the load power factor is not in our hand. It can have any power factor. It could be resistive, it could be inductive, or it could be capacitive, combination of all these three. So it could be any power factor. That means the voltage across the load and the current can have any phase displacement. So if we assume that the voltage is positive, that doesn't mean the current also will be positive. Means if I say the voltage is plus and minus here, that doesn't mean current always flows from positive to negative. It can also flow from negative to positive, or any with any phase displacement. That's what it means, any arbitrary power factor. That means we cannot have the voltage and current to have a same phase at any given point of time, right? Then the second thing is, irrespective of the direction of the current, the pole should be capable to be connected to T1 to T2. That means the switches what you're going to employ here should not have any limitation about the current that is being flowing through it. That is, irrespective of the current, that switch should be able to connect this pole A to either the upper throw or the lower throw. So there should not be any limitation. Similarly, irrespective, pole P2 should be able to connect to T1 or T2, right? Similar analysis goes here. Right. Now, if we analyze, that is during the positive half cycle, that is when you apply positive VDC here. So this is the switch. So anyway, this is open. Now, once the switch is closed, you should look at the current, and once the switch is open, you should look at the voltage, right? So we'll just look at the current. As the requirement says, the switch what connects here should have a current capability in both the direction, because we don't know what will be the polarity of whether the current goes into the load or from the load it is going to come out, right? So it should have a switch which can carry current in both the direction. So that is what is being marked here. And if you look at the voltage, since this point is connected here positive, the voltage is VDC with upper positive and lower negative. Similarly, upper positive, lower negative. So this is the blocking capacity required. So from this, what we learned is we should have a switch which should have bidirectional current capability, and which should block voltage VDC with upper positive and lower negative. Similarly, when you apply minus VDC here, again the same principle, the switch should have the bidirectional current, and again upper is positive and lower is negative, the blocking, again here upper positive and lower negative, right? So since this is connected to here, so what is the summary here? We should have switch which should have bidirectional current capability, and it should block the voltage of a single polarity, that is VDC. So how does the circuit look? Circuit looks something like this. So this is this I know, like everyone are aware of this H-bridge inverter, which is popular, like H-bridge, which is very popular single phase inverter. We have done a lot of analysis. So this is the reason why we have used a unidirectional voltage and a bidirectional current switches in an H-bridge inverter. Right. So the switches here have bidirectional current capability and unidirectional blocking capability, because that is what the circuit demands. So you can have any variety of switch, but this is the minimum requirement for this converter to have power conversion, like to convert power DC power to AC power, right? Now the next question is, does unidirectional blocking suffice as the application? Okay, now we saw that the switch what you are going to use should block the voltage in only one direction. So is it sufficient? How do we analyze, or how do we confirm? Yes. Now once the switch is on here, we have this and this switch on for plus minus VDC. If this is on and this is on, then what is the polarity of the voltage here? Plus VDC, this is minus, and here we have plus, and this is minus. Minus is nothing but the ground here, right? So this you can say as 0, plus and 0. So once this is on, then this VDC comes across these switches, right? Upper is positive and lower is negative. Similarly, when you apply plus minus, again here upper positive, lower negative, positive, negative. And we know that this is a voltage source type. The polarity of the voltage will remain constant irrespective of the current being drawn. So if this is the polarity fixed, then the voltage working of these switches is also fixed, because there is no way that this voltage is going to change. Means this will never become negative and this will never become positive. So unidirectional switches are sufficient for V to I. Like here, basically, we are converting V to I, right? Because we have a current type of load and we have a voltage source. So if this is the case, so what we did here, we have converted V to I. Now, what does the dual exist? Like how we saw in the DC-DC converter, buck and boost are dual of each other. Similarly, is there I to V inverter? Yes. So that is popularly known as a current source inverter. So this is known as a, so this one what we have here is a voltage source inverter, because the source is voltage and we have V to I conversion, and we have the dual of this, that is the current source inverter, that is I to V, right? So if it is a dual, then what is the structure? So we'll just try to see, like we'll quickly now assume that we have a circuit something like this. So we have V, R, L. Then what is the dual of this? So I hope the dual network is known. So what is the equation that governs here? V is equal to Ra plus L di by dt. Right. So what is the dual of this circuit? The dual is nothing but will replace the state variables here, right? So V gets replaced with I. I is equal to R will become G. I will become V plus L becomes C and I becomes C. Right. So this is the dual equation. That is, this is a KVL and this will be the KCL. If this is the equation, then how does the circuit look? We have a current source I. We have a G and we have C, and this is the voltage what we are seeing. This is the current what we are seeing here, right? So these two circuits are dual in nature. So why do we say dual? Because the state variable I here in this circuit and the state variable V in this circuit will have a similar response. That means in both the cases, I goes this way and V goes this way. So this is I, and this is V. Since the state variables have the same response, or they have the same characteristics, then the two circuits are said to be dual. Or in other words, if KVL of one circuit is same as the KCL of the other, or the mesh equation of a given circuit and the nodal equation of another circuit, if they are similar to each other, then they are said to be dual. With this in mind, can we have a dual of voltage source inverter? Yes. So how does the dual of a voltage source inverter look like? For that, we'll just take a half bridge example, so it will be easy to know, right? So you have two capacitors. The midpoint is taken. You have a R, and you have the switches here, right? These are unidirectional voltage and bidirectional current switches, right? So you have V by 2, and R, right? Assume this is the current. So this is a voltage source inverter, right? Half bridge. What is the dual for this? The dual of this, as I already told, will be a current source inverter, right? So the dual of that, what you have to do? You have to replace the capacitors with current source, right? And you have to replace the load with the source. And now you should remember that and you have a load connected here, right? This will be I by 2, and here you will have V minus or plus anything, right? So this is the dual of CSI, so dual of VSI, right? So you can see why is it dual? We had the capacitors replaced with current source. Same thing we did in the circuit. We replaced voltage with current. So we replaced the capacitors with the current source. Then we replaced the in a voltage source inverter. We used a unidirectional voltage, right? A unidirectional voltage, and a bidirectional current. Switch with here. What is the arrangement we have? Unidirectional current and bidirectional voltage. So again, these two are dual of each other. Then we had the source. We had the load here means we had the load here and source here. In case of VSI, now they are interchanged. So in every aspect, we have replaced the VSI with an equivalent dual part. And here you can assume here the current. You can assume that we have a source here of value I, same as the source we had V, and we had 2 V by 2s. Here we have I and 2 I by 2s, right? So if you apply KCL here, I by 2 plus I by 2 flows here, right? So we have I. So you can see this is a current source inverter, which is nothing but a dual of voltage source inverter. So they're basically dual of each other. Both are widely used. Current source inverters are generally used for hyper applications as compared to the voltage source inverter. And so that was half bridge. In full bridge, so this is the combination, right? So this is how the structure looks like. And if you can identify, you see a capacitor connected across the load in case of a current source inverter, right? We have a capacitor across the load. So why is this required? Because we should ensure, as I already told, we are converting I, and if the load here cannot be of I type, right? It has to be a V type, because we can have I to V conversion directly, and there is no intermittent stage here. So we should have a capacitor connected across the load to ensure that this forms a voltage type of load, because we have a current type of source. If you see the voltage source inverter, we had, let me draw, we had a voltage source and we did not had any capacitors connected here. So this was a current type of load. So V to I, there is no problem, but here we are having I to V, so we should ensure that the load is of voltage type. Then only we can have a converter directly connecting these two types, right? So this is the first thing. Voltage source converter is basically converting V to I, and current source is converting I to V, right? So this has to be remembered, right? Then we'll see whether we can see the simulation, right? So fundamentally, we saw the circuits of VSI and CSI and how they are structurally dual of each other, right? Now we'll just try to analyze voltage source inverter in a more deeper fashion. So what do we do? So this is what the ideally is expected from a voltage source inverter. We expect it to generate a sinusoidal waveform, right? Like a conventional generator. But this is not going to happen, because we told there is switching happening which is discontinuous, right? So this is the V0 what we generate a square wave. So this is what expected, this is what we are generating. Now what we'll try to see is, we'll try to analyze how far this square wave is similar to the sine wave, right? This square wave and this sine wave, what is the similarity, like how far they are same to each other. So that can be done using a Fourier series. Using Fourier series, the output voltage V0 is given by 4 by pi VDC sin omega t plus this, and it goes up to infinite terms, right? So what this Fourier series basically trying to say is, this square wave V0 is nothing but an addition of sources, addition of AC sources, addition of infinite AC sources, right? So V0, addition of infinite sources. If we assume this term as V1, V2, V3, V1, V2, V3, and Vn up to nth, right? So this is what the Fourier series is saying. Means this square wave you can achieve if you add sinusoidal voltages of frequency omega t, sin omega t with into this plus 1/3 of the magnitude with frequency 3 omega t. Okay, we'll turn this as V3, V5 with frequency of 5 omega t with frequency of n omega t, right? So if you go on adding the sources, then what you get is nothing but a square wave. So what it says is this square wave has sinusoidal component in it, and this is what we are expecting. We want sine of omega t alone, but square wave also has sine of 3 omega t, 5 omega t, 7 and many other frequencies which are called as the harmonics, right? So because they are the integer multiple of the fundamental frequency omega. We wanted the inverter only to generate sine omega t with some amplitude, but inverter in addition to this, it is generating this and many other terms. So how do we eliminate, or what do we do with this term? So what do we do is this. So that is called as pulse width modulation. So this is one of the pulse width modulation, basically the technique to make this square wave better, in the sense to we'll make this square wave very nearer to the sinusoidal waveform, right? So how it gets nearer to the sinusoidal, we'll try to see. Assume that we have a carrier waveform, the triangle, and we have a sinusoidal. If both are having same frequency, that is the carrier waveform, frequency of carrier, and the modulating waveform, that is the blue color waveform, are having same frequency, and this is what the output we get, that is a square waveform. And this is the FFT window which shows what are the harmonic component or frequency harmonic component, right? So the V carrier and VM has the same frequency component, that is 50 hertz. So this is the output. You can see we have 50 hertz, 150 hertz, then we have the next, that is the 300, like all odd harmonics here, right? So this is the output. Now we'll see what happens if we increase the carrier frequency to 300. Instead of a single triangle, we'll make it as a 300 hertz, and this remains the same. This is the fundamental what we want the inverter to generate. So we are trying to modulate the inverter, or we are trying to switch the output voltage so that the average variation of this will be sinusoidal in nature. We are 100% sure instantaneously we cannot generate the sine wave. So what we are trying to do is we are trying to generate the average variation of sine using the switching, right? So that is the basic idea. Inverter generates sine wave, but on an average basis, not an instantaneous basis. So we have carrier and the modulating waveform. So now we can see the carrier waveform is shifted to 300 hertz. So this is the component in the carrier. You can see the reflection here. That is the 150 hertz, and in between harmonics is reduced, and you can see the next amplitude, which is very powerful, appears at the 300 hertz. Now we'll increase it further. We'll make the carrier frequency 500. Then what happens? The carrier frequency component is here, and you can see output voltage harmonic also shifted to 500, and all other harmonics, means all other energy components, has become 0. What if we increase further? So we make the carrier frequency 1.5 kilohertz. You can see here, and the harmonic also shifted here. That means till 1.5 kilohertz, there are no energy components. There is no energy components in the output. So this indicates that the carrier frequency what you are going to choose will dictate what is the harmonic frequency that will be generated by the inverter. So the higher the frequency of the carrier, higher will be the harmonic amplitude, means the frequency what you are going to generate. And as we already told, VSI, we are going to have a current type of load. So definitely there will be L in the circuit, right? And what is the impedance of L? It is omega into L, right? So higher the harmonic frequency, higher is the impedance offered by the load, and hence the harmonic current because of that particular harmonic source is going to reduce. So that way the fundamental component gets stronger, means it will get strengthened, and it will be more sinusoidal in nature, right? So that is the advantage of increasing the carrier frequency. If the inverter operates at higher carrier frequency, the dominant harmonics also get shifted to that particular frequency, and hence you require a smaller filter to filter out these harmonics. That means you are increasing omega, so you can reduce L for a given XL value. If you fix the XL, And as the omega is increasing, you can reduce the value of L. That will reduce your size of the inverter or the filter. Right? What is this impact on the load current? You can see this is with carrier frequency 50 Hertz. So this is the load current. And this we expected it to be sinusoidal, but it is nowhere near to sinusoidal. When it is 300, we can see some variation. When it is 500 Hertz, so this is the load current. Even though the load current is having a pattern which represents sine wave, it is not sine wave yet. Then we have 1.5 kilowatts. You can see it is very nearing to the sine wave on an average basis with the ripple around it, right? So as you go on increasing the carrier frequency, the current becomes more and more sinusoidal in nature, but at the cost of increased losses in the inverter. Because as I told, none of the practical devices will have zero losses. They are going to have loss happening in every switching. So more the time you switch on and off, higher is the losses. So this is a trade-off. So depending on your filter size and depending on the loss, there has to be a trade-off so that you can achieve an optimum value where both the things gets satisfied, right? Then we see that the modulation index, yeah, this is a term modulation index, that is nothing but the amplitude of your modulating wave, that was a blue waveform there, and the carrier waveform, that is the triangle waveform. The ratio of this is called as the modulation index. It's similar to your generator, how we control the turbine to control the power. Here we control the modulation index to control the RMS value of the output voltage of the inverter, and this is linearly related to the output. So this is the VDC, the DC voltage is fixed, right? So depending on the modulation index, the output voltage RMS varies linearly, which can be seen here. So for modulation index equal to 1, you have the fundamental amplitude 100. For modulation index equal to 0.5, you have fundamental amplitude of 50. Right? So output voltage varies linearly with the modulation index. So this is just a simulation results. So what we saw till in the previous slide is that output voltage was swinging from positive to negative, right? Now using two modulating waveforms, we can have an intermediate value that is 0, right? That means, so this is your sine wave that has to be generated. So what we did previously, we switched it from positive, negative, positive, negative, positive, and it went on, right? So during the positive half cycle, if you see the sine wave, it is only having positive values. So there is no need to generate negative values at the output of the inverter, right? So what is the variation it has been done is, during the positive, we will generate only positive values, and during the negative, we will generate only negative. So that is the idea of pulse width, this particular modulating technique, that is called as the unipolar modulation. Here the output voltage will have positive and 0, then the negative we have 0 and the negative values, that is during the negative half cycle, right? So what is the advantage of unipolar modulation? We'll just try to understand here. So assume this is the sine wave instantaneous value that we are trying to realize on an average basis. So this is the sine wave, like you have a sine wave which goes something like this. For this particular time period, we'll assume it is constant for this time period, right? Now in bipolar modulation, so what is the bipolar modulation? Output voltage swings from positive to negative and back forth. In case of unipolar, during positive it is positive half cycle, it is positive 0, and negative it is negative half cycle, it is 0 and negative, right? So this is called as unipolar modulation, and this is called as bipolar modulation, right? Now, so this is the average value, means instantaneous we have to realize. And in bipolar, what do you do? In order to realize this on an average fashion, means this is the average value, right? So you will switch to VDC for some time, and you will switch to minus VDC for some time, so that in a time period Ts, the average value is this. But in case of unipolar, what do? You switch to VDC for some time, and you're going to switch to 0 for some time. In both the cases, the average value is same. But if you look at the instantaneous error, the instantaneous error is almost same. This is what you want, and this is what the inverter is generating. So this is the instantaneous error here. And during the negative, so this is what the expected, and this is minus VDC, that is inverter is generating. So this much is the instantaneous error. So you can see that the instantaneous error is lesser in the case of a unipolar modulation. So what does it mean? It means the waveform quality of what you are going to achieve in unipolar will be better because you are realizing a sine wave with less error, right? So the waveform also validates the same. So this is the output for unipolar modulation, and this is the current for bipolar modulation for a this is 1 kilohertz. So for a 1 kilohertz frequency, so you can see that current is more sinusoidal in case of unipolar, and it is not that much in case of bipolar. The reason is in unipolar, the approximation or the way in which sine wave is generated is more is very efficient. Efficient in the sense it is with less error. In case of bipolar, you have more instantaneous error. So what is the summary we can have here is if we have means this also refers to the quantization error. So if you remember the ADC operation, that is AC to DC your analog to digital conversion, you have something called as quantization. So depending on the level of the sine wave what you want to achieve, you have to switch between the two options what are there. If the instantaneous error is higher in the switched value, then it will give more distorted waveform, right? So that is the idea of multi-level inverter. So far we saw the fundamental operation. So what we are trying to do in multi-level is we are trying to achieve this sine wave variation with more and more quantization levels. So this is the idea. So you have a sine wave, right? In bipolar modulation, you achieved by switching between positive and negative, right? In unipolar, you did the same by switching between positive 0 and negative 0. In multi-level, you will do this by switching with various levels. So that means you have a sine wave, you are going to do this at different level that you are going to quantize. Using the quantization technique, you are going to achieve the sine wave, and you are going to switch between levels which are very nearby to each other. So that way, the output waveform quality is going to increase. So you can see this is the bipolar modulation, this is unipolar better than this, and this is the multi-level where you have intermediate level. So you can see the instantaneous error is lesser in each case, right? So here the instantaneous error is higher, and it gets lesser and lesser the moment you have many intermediate levels in realizing a sine wave. So in order to have these intermediate levels, you should have many sources and many switches that can switch to these levels, right? So DC addition and AC addition. What we are trying to do here is assume you have two DC sources and you have a load. Then how exactly we can interconnect these DC sources? So it can be done in two ways. One is called as the DC addition. So that can be done using. I'll just quickly run through this. So you have a switches here. Right. So this is a VSI, right? Drawn in a different fashion. Assume so this is your DC source 1. Then we have DC source 2. Right. So what we do now? The question is, if you have two DC source, how do you produce a multi-level output at multi-level waveform at the output? Right. So this is positive, negative. Positive, negative. Right. So what do? We'll connect the negative to the positive, right? So that way we can connect these two sources in series. Then what is the total output here across the terminal? So depending on the switchings, so this is S1, S1 bar, S2, S2 bar, S3, S3 bar, S4 and S4 bar, right? So this bar indicated they are negative of each other. So output voltage can be VDC1, or it could be VDC2, or it could be 0, or it could be VDC1 plus VDC2, right? Or it could be minus of VDC1 plus VDC2. Right. So this way you can have many combinations. Ultimately, you are going to generate 5 levels of voltage depending on the source voltage. Like they're of same value, say 100, 100. Then you can output will have 0, 100, 200, and minus 100 and minus 200. So you can have a 5-level waveform at the output. So this is called as a DC addition. You're doing the addition at the DC. Now assume you have only one DC source, then we have to, if you want to generate 5 level, then you have to go for an AC addition. What do we do there is, we'll take the 2 inverters, right? We'll take the outputs, and again the similar kind of inverter, the outputs, this will give it to a transformer. This is another kind of multi-level generation, and the transformer secondaries you are going to connect in series, and you have a load here, right? And this DC source feeds the both the inverter, means it is common to both the inverters. What we are doing here we added on the DC side, means using the switching, by connecting them in series, opposition and series aiding, you can realize these values. Here you will do the same, but you are adding on the AC side, right? So V01 and V02 both are AC waveform, and these two gets added, whereas you have a common DC. So these are the two variation what you can have in any, like fundamental variation what you can have in any inverter. Either it will be of a DC addition type, or it will be of a AC addition. So what we'll try to say is, if you go do the DC addition, now this is for 5 levels, you have 2 units, right? So the relation is number of levels minus 1 by 2. So this is the number of units required. Sorry. Number of units required. So 5 levels, you require 2 units. Now what if it is 9 level? Then you require 4 units. That means 4 units having 4 switches. So you require 16 switch, and you require 4 sources, right? For DC, if you go with the DC addition principle, for generating 9 level, you require 16 switches and 4 sources, right? So this you just keep it in mind. You require 16 switch and 4 sources. So in contrast to that, this was one of the topology that we had proposed in the year 2017, where we could able to achieve 9 level with only 10 switches, unlike 16 in the previous case, and 2 sources, unlike 4 sources in the previous case, and whereas we required only an additional capacitor. So this is the structure. I'll just quickly run through it. I think we are running out of time, right? So this is the capacitor here, and this is the switching table, right? So what is the principal idea is here is to have the charging and discharging of the capacitor over a cycle in a symmetrical fashion. You can see there are 2 charging states in the positive half cycle and 2 discharging states during the negative half cycle. So over a fundamental cycle, the total charge by the total charge that is put into the capacitor and taken out will be 0. That way the capacitor will maintain the voltage VTC by 4 on an average basis, right? So this was the experimental setup. These were the results. You can see we have a 9 level output waveform. We have 1, 2, 3, 4 and a 0 here. So 4 up and 4 down plus 1. So it is a 9 level, right? And this is the capacitor voltage. You can see it is balanced on an average basis, and it is without any sensors, right? So this is for a modulation index of 1, and modulation index, as we reduce the modulation index, number of levels gets reduced. So this is a 7, this is a 5 level, and then we have 3 level, and these are the variation, right? So research opportunities. So what are the things? So we mainly focused on inverters here, right? So 2 things can be done. One is on the topological advancement, and another is the modulation methodology. In the topological advancement, we have multi-level inverters. So why we call it as topological advancement? So the idea in multi-level inverter is using many switching devices and source, can we have an output voltage which is very nearer to sinusoidal waveform? So this is the idea. Inverter must generate ideally a sine wave, but it is not going to happen. If that is not going to happen, then whatever the waveform we generate, can we take it near to close, very near close to the sine wave? So that is the idea. And multi-level inverters are those which will do this using a kind of a quantization technique. So on the topology side, there are innumerable topologies that are available in the literature. So if one has to work in this area, so this is the very broad area what we work on. So far we have proposed many topologies which are well accepted and that available already in the as publications, right? So, so in this, what we do, we'll try to come up with some modification to the circuits which are already there. So in that way, which can achieve the same result with maybe lesser number of switches or lesser number of components and many other things. So that is one of the area which can be looked into in the inverter side, right? So to come up with novel topologies, right? To come up with novel topologies with high reliability. So reliability is important, and efficiency, right? Then we have renewable source integration. So this is another area where we need not much worry about the inverter structure and all. The important aspect here is how well the renewable sources being integrated can be controlled. So that is the challenge here, because as I already told, the solar PV and the wind are all intermittent in nature. So the power input from them constantly varies. So how do we get the maximum power at any given point of time? So that is the MPPT techniques what we already have. And when you integrate this into the grid, there are other challenges that inverter, in addition to the power waveform or in addition to the fundamental waveform, it generates harmonics. So how do we control these harmonics? So that is one of the issues. So one can look on the filter optimization, or one can look at the control aspects that are required to have stable operation with the grid, right? Then we have smart grid. In smart grid, we have variety of sources like batteries. Then we have energy sources. Then we have storage. That is the battery. You can have ultra capacitors, SMEs, and many other things which are going like all together. They'll be trying to make the system stable, right? So one can look at how to manage the energy between these sources and the storage. So what is a better management system? So one can develop power management or energy management system in case of smart grid, like when exactly particular storage can be brought in, or when exactly it has to be taken out of the system. All those things comes under the energy management. Then another thing is the application specific. It could be like, as I told, in the aircraft application, you require 400 hertz power supply. So how here the criteria is the power density. Whatever the converter you develop should have very high power density, so that with less space it can do the same power operations, right? So those are application specific. Then the second part is the modulation methodology. Waveform quality means in a given structure. So in a given structure, like the structure is the same, inverter remains the same. Then what modification you can do on the modulation side so that the quality of the waveform being generated is improved. So that is the waveform quality. Here we have your selective harmonic elimination or selective harmonic minimization techniques, which are the advanced methods of eliminating a certain harmonics using a proper sequential switching. So that is what we can look at waveform quality improvement. Well, we will not much worry about the structure, right? Then we have DC bus utilization. So if you look at any inverter, the maximum voltage what you get is VDC, that is whatever is there on the DC source. If you have 100 volts, then the maximum peak voltage what you get is 100, right? So DC bus utilization is there a way that we can increase this value using either some structure or some switched capacitors in between? That is what we are looking into in the recent days, that how to use the switched capacitor technique to boost this input voltage, and we to have a higher voltage on the AC side without having a conventional DC to DC boost converter. So if you go for a DC to DC boost converter before the inverter, then it is a two-stage conversion, efficiency goes low. So in a single stage, can we have this input DC voltage boosted, and so that we have a higher AC voltage? That is what we are looking into. That is the DC bus utilization. Then improved efficiency, is there a way that we can operate the system with a better modulation technique that gives higher efficiency? And improved reliability, that is we can come up with some fault tolerant techniques so that the inverter will able to sustain its operation against the various faults that might happen, like open switch fault or short circuit fault, and mal-operation of any of the device. So basically it is a kind of developing a control system which will take care of these faults, and it will still try to maintain the operation of the inverter without bringing the system to halt. So these are the few areas that I thought of to share, that where we have possible research opportunities. We basically work on the inverter structures and the DC bus utilization. So these are the two areas which in particular we look into. Right? And these are the references that were taken. And yeah, thank you.
Thank you, sir. Thank you for your wonderful session. Now, forum is open for questions.
Yeah, ma'am. Okay, ma'am, can you read it out or? Yeah, sure. Thank you. Okay. So the power interface basically, I mean to say, is, let me put up that slide again. Yes, is basically a structural combination, or in simple words, we can say it is a way in which switches and the energy elements are arranged so that, assume you want to DC to DC conversion, means you have a AC source and you want a load which you have a load which requires DC. Then what interface you have between, or whatever the in between component or in between system you have which connects these two is called as a power interface. So main three elements is the switches, then capacitor and inductor in power electronics system. Yes, ma'am. Next question. Well, switching transient, I mean, you need to say the transient that happens. Yeah, of course, whenever there is a switching, the circuit enters transient and then it gets into steady state. But these transients are very, you can see at a very faster rate because the switching frequency itself is very high. So the switching transients might result in, if there is no proper snubber design and all, might yield in higher voltage spike or higher current, but that has to be taken care. So of course, yes, when there are switching conditions, when switching happening, transients do happen. Huh. And why? Okay. So I think I am not. I have much idea on the wind system because we mainly work on PV and PPT, and it's better you can ask the question to Vijay Kumar sir, who will be handling on the wind system. So he'll be a better person to answer this. So sorry, I don't have much idea. So you can you can repeat the question in during that session. So he'll be Vijay Kumar sir session. You must attend, right? Well, current source inverters, yes, they do have practical limitations. One of the key limitation is the maintaining the inductor current. That is the key challenge there, because at any point of time you should not break that circuit, means the inductor current. So, but we do have inverters like you have like CSIs are using drives. If you look at high power drives, you have CSIs there, and now CSI also being used for PV application because you have an inductor there, and PV source it requires, if you draw continuous currents from the PV, then it results in better efficiency. So even applied for PV systems. So you can look into motor drives and you can also look into the PV application. So current source inverters, yes, they are not that popular as that of VSIs, but still, because the key advantage of CSI is it has a boosting capability, right? Because it is doing I to V conversion. The moment you do I to V, the V will be higher than I. And similarly, when you do V to I will be higher than the input, whatever the current we have. So yes, in drives and PV, it is used. DC link inverter. It like I, I don't know exactly what is being asked, but DC link inverter, any inverter will have a DC link means or a DC bus. It is just an alternate word, I guess. That's it. Effect on loads. Like they are connected in what fashion? That it depends on that. If they are connected in series, then the voltage will be higher. If they are connected in parallel, if they are of same magnitude, it will be the same. I don't know what exactly the question is, but if they are connected, it depends on how you are connecting them. That's it. The effect. That's it. Hmm. Well, you have in HVDC systems, you have multiple rectifiers. You have 24 pulse, then we have 12 pulse rectifiers. So those are being used, and mostly they are thyristors or GTO based. So definitely there are in like applications where they are using multi-pulse rectifiers. This is what being used, multi-pulse rectifiers. Like yeah. See, again, it depends. See, if you don't want, or if you want to obey KVL, you should not connect two DC sources in parallel of different magnitude. So yes, you can connect them in series. There is no issue. So try to obey KVL and KCL. You can do whatever you want. Okay. Instantaneous error is higher in bipolar, and yeah, see, instantaneous error, like what I can, instantaneous error is higher in bipolar and it is lesser in unipolar. So that is what. And this instantaneous error, it keeps on varying because at every point of time you will not be switching, or you are not going to average the same value. The averaging value is going to vary, and it is going to vary sinusoidally. So instantaneous error also varies. So if you have to see the average instantaneous error in that case. So it is higher in bipolar and lesser in unipolar. Yes, ma'am. See. In two ways, one way external to the inverter by designing a proper filter, that is externally. Internally, by modulating the inverter in such a way that particular harmonics get cancelled to each other. We have selective harmonic elimination and minimization technique. There, what you do, you are going to see again. Let me tell you, the harmonics what you generate from the inverter depends on at what point you are going to switch the inverter. So, if you switch at say time t1, then you will get certain harmonics. If you switch at t1 plus some delta, you will get certain harmonics. So by controlling that switching, you can control or you can eliminate few of the harmonics, and it is very important to eliminate the lower order harmonics because they'll have higher amplitude. So they will see very low impedance in the network. So lower order harmonics should be eliminated. So two ways, either you do internally by controlling the switching or you do the filter optimization. Switching, I hope the switching transients, you mean to say this voltage spikes and currents, right? So it is always desired to have snubbers, right? So in power electronics, we should always try to have an inductive turn on and capacitive turn off. That what I mean to say, whenever you're switching on, you should see an inductor so that the current will not rise, and when you're turning off, you should have a capacitive nature. So you should have proper snubbers so that there won't be any voltage spikes, and you should have an induct kind of, I can say it also takes care of the current spikes. So that is the only way you can have those, or you should have a proper switching so that there won't be any transients happening which are of higher magnitude. Yeah. See, practically, you cannot have an open loop current source inverter. You can have a DC source and an inductor, and you should have a sensing mechanism, and you should keep on tracking the current, and you should have some control system which will maintain that current. So practically, it is difficult to realize CSA, but it is not impossible. So you should have a sensing mechanism there to have the current, a continuous current in the inductor.
Thank you, sir.
Thank you, Sandeep sir, for your wonderful session. Starting from the basics of power electronics, devices, its characteristics, and finally up to applications. Hope this session will help the participants to know the basics of power electronics and their applications, because this is very important when you go for the next session, like power electronic interface for the great electronics interface for renewable energy sources and all. So thank you, sir, for information, education, and providing such valuable information to the participants. Thank you all.
Thank you. Thank you all. Yes.
Thank you. So the feedback from your chat in YouTube. So kindly fill it. Make sure that all the details are correct. Your name, email ID, and institution, because depending upon that only the certificates will be issued. So after the feedback, 30 minutes of 30 minutes. Thank you all.